Okay, today we continue to talk about rainfall runoff modeling, and I anticipate that today the lecture is quite technical, and so be patient. And I will also give you some details about what I may ask you at the final exam on the specific topic that I'm treating today. And please feel free, even that it's a bit technical, feel free if you would like more details on what you are expected to study rather than what you are expected just to know with a broad view, feel free to ask me. But I will try to be very exhaustive in explaining to you what I'm expected that you learn by memory and what I'm not expecting. And basically, what I would like to do today is to start putting rainfall runoff modeling within a physically based framework. Namely that for now, I introduced just one rainfall runoff model, which is the rational formula, which is empirical. And while today I would like to move to a more theoretical treatment of the physical basis of rainfall runoff modeling. And I already anticipated to you a key concept, namely that the conservation of mass, energy, and momentum are always satisfied in fluid mechanics. And given that we are dealing in hydrology with movement of water, we are basically within fluid mechanics. So I already anticipated to you that the physical laws underlying hydrological processes basically imply conservation of mass, energy, and momentum. And in fact, if you think to the rational formula, which we introduced, which is an empirical formulation, which I expressed, I think, in this way, where this is rainfall intensity, and then you know that capital A is the area of the catchment, and C is the runoff coefficient. In this formula, which is empirical, there is an implicit assumption of conservation of mass. Because if you express the river flow, depending on the rainfall intensity, it means that you are assuming mass conservation implicitly. And why I'm saying so? First of all, let's consider that mass conservation doesn't imply that you don't have any losses. Imply that you are able to write a balance equation which is satisfied, in which balance equation you can introduce the losses. Like conservation of energy, for instance, if you think to hydraulics, the loss of energy is accounted for. So conservation should not be interpreted in a strict sense that you don't consume energy. Energy can be consumed, but conservation means that you are able to write a balance equation. So in this case, the fact that you have the runoff coefficient, which means accounts for water losses like evaporation, doesn't mean that you don't have a mass balance here. If you look with a broad view, this is a mass balance equation because it expresses the river flow has a linear function of rainfall, which means that the output from the system in terms of river flow is written as a linear function of the input to the system, which means that the mass is conserved. And losses are accounted for by means of the runoff coefficient C. So you see that here, time by time, mass is conserved, even though this is an empirical relationship. This shouldn't surprise you. If you have an empirical formula that works to describe a physical process, it's obvious that if it works, the empirical formula should not contradict the physical laws underlying the process. So if we accept that mass balance is valid in this particular case in rainfall runoff modeling, we should expect that an empirical formula describing rainfall runoff modeling, at least implicitly, should respect mass balance, cannot contradict it. Sometimes, to identify in an empirical formula the implicit and underlying physical basic is challenging, and this is what I would like to do with you. We have in rainfall runoff modeling many empirical formulation, and this empirical formulation, of course, describe a physical process for which some physical laws are met. And what I would like to do with you to make the whole treatment clear is to fit all the possible rainfall runoff relationships, including the empirical ones, within the physical concept, so that you understand the physics, and then you understand that you can describe physics with mathematical models that are specifically physically based, namely that they identify the physical law and describe each physical law with a mathematical relationship. But also I would like to show you that even if you take an empirical relationship, this should well describe the physical process, which means, in this case, to expect the mass balance. So you see that the treatment is a bit, maybe a bit technical, but what I would like to do is to make this clear. So this is the only model that we brought into play so far, and I would like to emphasize that the mass balance equation here is respected. Okay, so these physical laws which I'm mentioning, the mass balance equation, the conservation of energy, conservation of momentum, and please keep in mind that the mass balance equation is also called continuity equation in some textbooks. This equation, these conservation equations, then are a fundamental tool for us in hydrology to describe processes. And they can all be derived by a fundamental theorem that applies in fluid mechanics, which is the Reynolds transport theorem. And there are slides in my website which you can download. Today I'm not using slides, I'm just writing on the blackboard, but what I'm writing on the blackboard today more or less is described in the same way by my slides, so you can use the slides as a reference. And in my website in particular, you can find mention to the Reynolds transport theorem on the slides, on rainfall runoff modeling, but I also uploaded an additional document, a PDF file, which I found on the web, which provides a clearer description, because the slides are not very descriptive. They just report the Reynolds transport theorem in mathematical forms, but they don't describe it. So, what is the Reynolds transport theorem? First of all, let's clarify that this theorem refers to fluid mechanics and then to the transport, to the movement of fluids. So the theorem refers to a body of fluid, refers to a system which is a body of fluid which is moving. So basically we decide to identify a body of fluid whose movement we want to describe. This is in general. You can, for instance, think of a pipe. I take the example of the pipe because it's very simple to understand. You can take the example of a pipe where you have some water entering the pipe from one extreme, and then from the other extreme of the pipe you have water flowing out. And if you look at the pipe at a certain time instant, you have some fluid inside it. And this is the body of fluid that we want to describe. This is just an example. Let's assume that we want to take as body of fluid the amount of fluid that is contained by the pipe at a certain time. And this is our system. we want to describe what happens to this fluid. This body of fluid includes a certain volume of fluid. And there are physical properties that you can identify for this body of fluid, like the mass, like the energy, like the momentum. These physical properties are proportional to the volume of the fluid. So you can say that the mass within this pipe, the mass of the system of this fluid, is proportional to its volume through the mass density. So these properties, which you can identify for a body of fluid, which are physical properties, which are proportional to the volume, are called extensive properties. One example is the mass. Another example is the energy. The energy is proportional to the volume of fluid. Another example is given by the momentum. These are extensive properties. You can express the same properties in terms of density. If you express the density of these properties for unit volume of fluid, you obtain what are called the intensive properties. Mass density is an intensive property. So you have extensive property for the body of fluid, which depends on the volume. The intensive property doesn't depend on the volume because it's divided. The intensive property is derived by dividing the extensive property, the corresponding extensive property, by the volume. So again, an example is the mass and the mass density of the fluid, for instance. Let me write down rho is equal to m divided by v. So what does Reynolds transport theorem say? Let me write it down. The Reynolds transport theorem at the left-hand side includes the total derivative along time of a given extensive property of the system. Again, keep in mind that the system is the body of fluid that I want to describe, which is moving. So at the left-hand side, the Reynolds transport theorem contains the total derivative along time, again, of the extensive property. You may think of the mass again. You may think at the mass of this body of fluid. Let me anticipate that if you think at the mass of this body of fluid, this is not changing in time. Because if you identify a body of fluid that you want to study, this is your body of fluid that you define. And if it moves, it cannot change the mass. Unless you put some other mass in, which means that you don't preserve your body. You change body fluid. So if you don't add more mass or you subtract mass, the mass cannot change. So for a body of fluid which is identified, think of a lake, for instance. You say, I want to study this lake. Means that you want to study this mass of water which is in the lake. It doesn't change in time. Okay? It may evaporate. But if it evaporates, it means that it's no more in the lake, but it's somewhere else. But it's still in the body of fluid. If you want to study this body of water, water that evaporates means that the body of water is no more in the lake, in the atmosphere, but the body is still the same. So there is a difference between the body of fluid and the tank, for instance. In rainfall modeling, the body of fluid is the water which is in the atmosphere and rains and reaches the catchment, and then you find it in the river. It doesn't change the mass. What changes is where the water is. So in this case, if I focus on the body of fluid, I'm not focusing on the catchment. I'm focusing on the water. Okay, so again, Reynolds transport theorem at the left-hand side includes the change, the total derivative along time of one extensive property of the body of fluid. I told you that the treatment is a bit technical, so make an effort and it will become simpler as I move along the lecture. Now, what happens in this body of fluid along time? It moves. So, the pipe doesn't move. The fluid moves. So, for instance, after a certain delta t, I find the same body of fluid which moved. And it can be like, now I'm sorry that I don't have colored chalks, but I hope that I can make you understand. So the same body of fluid maybe moved. In general it can move, it's moving. So maybe it moved. The pipe didn't move. It moved. And we want to describe this movement. This is our objective. Our very engineering problem is to describe this movement of the body fluid. Because if we are able to describe the movement of water, then we describe rainfall of modeling. And usually, in order to describe the movement of fluids in fluid mechanics, one refers, and especially in hydrology, we refer to conservation equations, which are applied on a fixed volume. The body of fluid moves, but we want to apply these conservation equations to a fixed volume because it's simpler. And this is called the control volume, that for us in hydrology is typically the catchment. So basically we have this water moving, in our case from the clouds, and then it's under the form of vapor, and then it condensates, it rains. It's difficult for us to describe the movement of the fluid in this moving environments and the different states, vapor, maybe snow, maybe water, maybe ice. And therefore, a way which we usually choose is to apply this conservation equation to a fixed volume in time. For us, it's the catchment. And therefore, here you can see a difference between control volume and system. The system is the body of fluid moving, which you would like to follow. The control volume, namely the region of space where you apply the conservation equation, is fixed. So again, we say too difficult to follow water from the clouds, from how can I apply conservation equations for water that changes state and moves at a global scale. It's too difficult. It's better to apply the conservation equation to a fixed control volume, which is the catchment. And take this opportunity to learn this terminology, control volume, system, because, you know, it's a terminology that is important for an engineer, at least to better understand theory. And maybe you already know this terminology from your studies of fluid mechanics, hydraulics, and take an opportunity to clarify your ideas. I know this is not easy because we are not mathematicians, we are not used to complex abstractions. Okay, so the Reynolds transport theorem then wants to describe the change, the rate of change, left-hand side, of this extensive property. And then the rate of change can be expressed as an integral extended to the control volume of the partial derivative along time of the product between mass density of the fluid and eta, which is the corresponding intensive properties of capital N. The V. And keep in mind, this is how I write in a simplified way the theorem. There are some more rigorous texts which display here a tripole integral, because I'm integrating over a volume. Of course, if you want to integrate on the x, the y, the x, the y, and the z, you need a tripole integral. I just use this simplified representation. What does it mean, this term here? Partial derivative over time of the product of the intensive property times mass density of the moving fluid times the elementary volume. And what does it represent, this term? First term in the right hand side. It represents the facts that when you observe your body of fluid, independently of the fact that it moves, there could be, during time, ongoing, a change of mass within it. There might be a change of mass. What could be a change of mass? Think like if you are injecting, while you start studying this pipe, there might be somebody who is injecting some fluid in. And therefore, this is a source term. This is indeed an opportunity to include a source term, which means that besides the movement, which brings into the control volume mass and brings in and out mass, besides the movement, you may have source terms. And this is, for instance, a term that is used when one wants to describe water quality in rivers. Water quality is determined by the transport of the contaminants along the river, but there could be a sewer system, a fognatura, releasing contaminant in the river. This is a source term, meaning a source of the extensive property which is not due to the fact that the fluid is moving. So in the control volume, there is a source term, an injection or a withdrawal of the extensive property, which is not due to the fact that the fluid moves. Okay? And then we have also a change in the extensive property of the system because the system is moving. And therefore you have this integral is extended to the control surface, which is the surface surrounding the control volume, and takes into account what? Takes into account the fact that now you are referring to the control surface, and there is an extensive property, a quantity of that extensive property, which is entering and exiting from the control volume. So given that you want to study the change in extensive property of the system, but you are integrating on the control volume, you have to take into account the part of the system that comes out from the control volume. So the control volume gives to the system, for instance, some mass, because you have some mass of the system that is given by the control volume to the system, and at the same time you have some mass entering the control volume which is not part of the system. And you have to account for that because you are integrating on the control volume. Then, let me write here what? Again, the product rho eta, which multiplies the velocity of the control surface times scalar product, the outgoing normal vector, outgoing unit vector, normal unit vector which is versore normale uscente, outgoing normal unit vector to the control surface, the A, or the S, meaning elementary area. So, what does it mean, this term? First of all, let's forget for now that here you have the velocity of the control surface. This term aims to compute the fluxes of the extensive property, through the control surface, the surface surrounding the control volume. And therefore, basically, you take, in this case, the velocity of the control surface, because in general, the control surface could move. I anticipate that this term we won't consider it, because in hydrology, the catchment, the control volumes are usually fixed. So, but for generality, for the sake of generality, I just want to show you also this contribution. If you have the control volume which is moving, for some reason, you can account for it, and then this is the velocity of the control volume. You need to multiply the velocity scalar product for the outgoing normal unit vector, because you want only the component of the velocity which is perpendicular to the control surface. Because if you have some fluid which is crossing the control surface in this direction, you want to consider only this component, only the normal component of velocity, because of course it's what matters for us, because it's the component that brings the fluid out of the control surface. We don't want this component of the velocity which keeps the fluid in the control surface. So we want the normal component in the control surface, and therefore we take the scalar product and then we multiply velocity for the product between the intensive property and the mass density of the fluid. And as I said, this term is usually neglected in hydrology, but we have to consider another term which is exactly the same with only one difference. So rho eta, the vector now is the vector of the velocity of the fluid relative to the control surface. And if the control surface is fixed, then this is the velocity of the fluid. If the control surface is moving, then you take the relative velocity. Again, times n in the S, in the A. This is Reynolds transport theorem. So let me put a big rectangle here. And this is the form of the theorem that you see on my slides. And let me say that I'm fully aware that for you it's a bit problematic to distinguish the system from the control volume. I know. And let me say that from a practical point of view, you could avoid understanding this. It's not necessarily needed. You may just take that in the catchment, in your fixed control volume, there is conservation of mass, energy, and momentum. This is what is useful for us for moving forward. This is the concept that you need to take. But I would like also to provide you a physical explanation. Why this applies? It applies because for in fluid mechanics there is general theorem, which is Reynolds transport theorem, that in general applies to systems, moving systems, and it is for practical reason applied through integration over a control volume. So I wanted to give you the explanation. This is really uncommon. I think usually as hydrology is taught in Italy, the concept is not taught in Italy usually, because hydrology in Italy is taught in the Faculty of Engineering typically, and you know it's taught as an applied science. Taught means the past of teaching. I'm not not sure the pronunciation is correct. And it is taught as an applied science, but abroad, in the university abroad, they start right from the Reynolds transport theorem, because they want to make clear the physical basis. And this is what they would also like me to. And then what should you learn from this? What can I ask you at the exam? Sometimes, if I realize that the student is very good, I ask the student sometimes to write down the Reynolds transport theorem, which means that it must be learned by memory. Because I didn't start from basic principles. There are other theorems before the Reynolds transport theorem. If you go to Wikipedia, for instance, they provide a proof for the Reynolds transport theorem. So basically, again, I may ask you, if you are very good, to write down the theorem and explain to me what does it mean, this variation here. And one should say, this is a total derivative over time that applies to the system, and it's expressed in terms of variations computed over the control volume. On the left-hand side you have the system, on the right-hand side you have the control volume. And that's it. And then, of course, I may ask you, what does this imply? Why we call into play the Reynolds transport theorem? And one should say, just because it's the demonstration, it allows us to prove that mass, energy, and momentum are conserved in the system, and it allows us to compute these conservation laws on a control volume. It tells us, the Reynolds transport theorem, that we can impose these conservation laws by integrating on a control volume. And also, if you think of it, it also explains why mass is not conserved. If you, strictly speaking, I said before, mass is conserved because you account for a loss term. This explains to you why you have to account for a loss term, because you refer to a fixed control volume and then you have loss of mass inside the control volume. So if you want to impose mass conservation, Reynolds transport theorem tells you that mass conservation applies to the system, and if you refer to a control volume, then you have to include the famous source term, which can be also a loss term. Okay, so basically, in the PDF that you find on my website, you can find also an application of the Reynolds transport theorem at mass balance, energy balance. I don't want to go into the detail. I just would like to go a bit into the detail, just a bit into the detail, sorry, by referring to mass balance, because it's very simple. If we refer to mass balance, we can say that the mass balance, the variation along time of the mass of the system is zero, because of course the mass of the body fluid doesn't change, I already told you. And therefore, what Reynolds transport theorem tells me is basically that if I have a difference between, in the control volume, between inflowing and outflowing mass, okay, these two terms, let's forget about this. But this term here, let's suppose that is positive. This means that I have more mass flowing out of this control volume than entering mass. Because if this is zero, it means that what enters is what exits. If this is positive, it means that the normal is outgoing. So if it is positive, it means that I have more mass flowing out than mass coming in. And therefore, Reynolds transport theorem says that this means that you have a change of the mass contained, change in time. At the same time, you have a change in time of the mass contained in the system, which is of course trivial. Okay? If at a certain time you look at this pipe and you see that there is more water flowing out than water entering the pipe, it means that you have the mass in the pipe that is decreasing, which is trivial. It's trivial application of conservation of mass. And the theorem, another interesting thing that may tell you, which is also very trivial, let's suppose that you refer to static conditions, steady state. Steady state means that the derivatives along time are null, are zero, which means that this term here goes out. Then, what tells you Reynolds transport theorem? It tells you that if you look at the pipe at any time, you have the same quantity of entering flow than exiting flow. Because you cannot have a change of mass, and therefore it means that the inflow is the same as the outflow, which is also trivial. We know also from hydraulics, if you look at a river in steady state, means that you cannot accumulate mass along the river. In steady state you cannot. And therefore, if you look at the river ridge, the river discharge which is entering the river is the same discharge that exits from the same river ridge. Okay, that's it. Now, let's forget about application of the theorem for conservation of energy and momentum. Let's just remember that it's possible to apply the theorem to derive conservation of energy and momentum. And let's remember what I said last week. I said the number of conservation equations that you need to apply depends on the model, because it depends on the number of unknowns. So we have for sure an unknown, which is the river flow. But we might have more unknowns. For instance, we may need to describe state variables like the storage of the catchment. And therefore, if you have more unknowns, you have to call into play more conservation equation. So basically, one starts with the conservation of mass, which is the most obvious and easier conservation law